Our planet has been struck by a series of disasters that wiped out 99% of all species that ever lived. But if it hadn't been for these catastrophes, none of us would be here at all. 65 million years ago, an asteroid the size of Everest smashed into the Earth at 60 times the speed of sound. It triggered one of the greatest mass extinctions the planet had ever seen, and the death of the dinosaurs. This is the story of that great impact. Our planet is around 4.5 billion years old, and a lot has happened in that time. It's tough getting a handle on such an enormous period. So to put it in perspective, imagine the whole of Earth's violent history compressed into a single day, represented by a clock. At midnight, the planet formed. At 11:38 in the evening, the Earth suffered a catastrophic cosmic impact. A strike so large it blasted billions of tons of debris into space and set the whole planet on fire. It triggered a chain of events that wiped out 70% of all life on Earth, including the dinosaurs. It was an event that changed the course of evolution and led directly to the emergence of mammals and eventually humans. But how do we know what happened? Over many years, scientists pieced together a series of clues from around the world to build a detailed picture of the day the dinosaurs died. This is the Red Deer River Valley in the Canadian Badlands. Here, paleontologist Phil Currie hunts for clues to one of the most violent chapters in Earth's history, the last great mass extinction. Currie searches for the fossilized remains of the last of the dinosaurs buried within the valley rocks.
The wonderful thing about these badlands is you can go almost anywhere, and at specific levels you can actually find bone in great abundance. This was picked up in less than 10 minutes. And we have things like whole claws, sometimes whole teeth. Basically, along the Red Deer River, we have 10 million years of dinosaurian history represented. And at each level, there are different dinosaurs.
These layers of rock represent millions of years of evolution. The deeper the layer, the further back it is in time.
Well, as you can see, the rock here is actually in layers. In a way, it's kind of like looking at a book from the back forwards. Each one of these pages, of course, represents a different page in the history of the Earth.
Somewhere in these layers lie clues to the death of the dinosaurs. Several feet below the surface is a layer that's intrigued scientists for generations, the Cretaceous Tertiary, or KT boundary.
This is exactly what I was looking for. This is where we have the Cretaceous Tertiary boundary. And this is the area that for a long time we suspected would tell us something about the extinction of dinosaurs, because below the layer we have dinosaurs, and above the layer we have no evidence of dinosaurs at all.
The layer dates to the same time period as the mass extinction that wiped out 70% of all life on Earth.
So this appears to be the smoking gun. This may be the layer that indicated that there was a catastrophe 65 million years ago.
The KT boundary extends far beyond the Canadian Badlands. Scientists have found this same layer all over the world. Below it, fossils from countless species. Above it, 70% of them are gone, including the dinosaurs. Nobody knew what caused this mass extermination until clues emerged 5,000 miles away in southern Europe. Zumaya Beach, northern Spain. Hidden within these spectacular cliffs is evidence of what scientists believe wiped the dinosaurs off the face of the earth. Almost 30 years ago, biologist Jan Schmidt came to these very cliffs. He was investigating what wiped out the dinosaurs and was one of the first to think the KT boundary layer might hold the answer.
I started to analyze the rocks chemically, approaching the KT boundary right there. Because I thought there must be something hidden in the rocks to tell the story how they got extinct, why they disappeared.
What he discovered shocked the scientific world. The samples contained an extremely rare metal, iridium. That is, it's rare in rocks on Earth. Most of the Earth's iridium is trapped 4,000 miles below ground in the planet's core. But it is found in meteorites and asteroids.
And when you find a high abundance of iridium, you know you have a clue to extraterrestrial material. It has to come from outer space rather than from the surface of the Earth.
There was only one conclusion. A very big object must have hit the Earth. The iridium suggested that 65 million years ago, a massive asteroid hit the planet at the exact same time as the death of the dinosaurs. Many scientists were now convinced they had the murder weapon, a catastrophic asteroid strike. But to prove it, they needed to find the crime scene, the site of the impact. So scientists began a global search for an impact crater. By measuring the worldwide spread of iridium, they estimated that the crater must have been enormous, around 125 miles in diameter.
The problem with iridium is it's within the meteorite, but the meteorite is totally vaporized, and the iridium is strewn out over the whole world. It doesn't matter whether you're here or there on the surface of the planet, you find the same amount of iridium. So it doesn't tell you where to look for.
The scientists knew there had been an impact, and they knew it was big. But finding it was tough, because millions of years of erosion had wiped away the evidence of the impact site. It would take a combination of luck and sheer perseverance to find the dino killer. 11:38 p.m. on our clock of the Earth's history, 65 million years ago. 70% of all life on the planet has been wiped out, including the dinosaurs. Scientists thought this could have been the result of a cataclysmic asteroid impact. But they had no real evidence of an impact big enough to cause such mayhem. To prove it, and to build a picture of how the dinosaurs died, they needed to find the impact crater. Dan Durda is a NASA planetary scientist. He specializes in the aftermath of massive cosmic impacts. And where better to come than here? One of the world's most spectacular asteroid craters. Meteor Crater, Arizona. The impact that created it happened just 50,000 years ago. The asteroid that struck here was only 150 feet across, yet it created a crater 3/4 of a mile wide and devastated an area the size of Los Angeles. Meteor Crater is many times smaller than the crater that would have been left by the KT asteroid. But it demonstrates the enormous power of even a relatively small asteroid strike.
If a meteorite the size of a large house could make a crater of this size, imagine the devastation wrought by the impact of an asteroid the size of Mount Everest. That's the scale of the KT impact.
Meteor crater is a key clue in the search for the KT strike, because buried in its walls is evidence of how cosmic impacts transform stone.
That immense impact released in energy, our modern estimates are something on the order of 1 to 10 megatons. That's the scale of the largest nuclear devices we've ever detonated. That immense impact excavated millions of tons of rock. It peeled open the desert like the petals of an immense flower and sprayed blocks of ejecta, huge masses of rock the size of a small house, for miles in every direction out into the desert.
The heat and trauma of the impact was enough to transform rock itself, shocking and pulverizing individual mineral grains.
One sign of the violence of an impact event like this can be found in the rocks themselves. This is Coconino sandstone. It's a pretty solid sandstone. It's made out of quartz grains that have been cemented together. When this rock was shocked in the impact itself, it was pulverized and broke those sand grains down into a much finer material, almost the consistency of flour. You can see here what the impact has done to that material, which has now been cemented back together in the walls of the crater. Very violent event that can turn rock into flour.
This dramatic transformation was a vital clue in the search for the location of the asteroid strike. It pointed the scientists in the right direction. Following the trail, Dan Durda flies north to Trinidad, Colorado. He examines levels of minerals in the KT boundary line. The layer contains tiny mineral crystals, similar to the ones at Meteor Crater, as small as grains of salt. It's quartz, but that's not why it's interesting. It's interesting because something smashed it to pieces.
So here in the KT boundary layer, this thin white clay layer deposited, we find evidence not only of the iridium, which was the original signature that something funny, something extraterrestrial is going on here. This is that layer where we also find the shocked quartz.
Shocked quartz is created when quartz is smashed by an extreme force at speeds exceeding thousands of miles an hour. Only one natural phenomenon packs enough punch to shock quartz: an asteroid impact. These tiny grains seem to confirm that the asteroid that hit the Earth was colossal, and the impact took place around the time of the dinosaur extinction. But the quartz grains also took scientists a step closer to the impact site. While the iridium was spread evenly around the boundary layer, the shocked quartz was not.
As we look at the thickness of this layer, here in Colorado it's about a half an inch thick or so. As we move to the southeast, however, that layer gets thicker and thicker. It grows into meters thick as we move toward the southeast, toward the Caribbean. Probably a pretty good indication that, that the impact occurred in that region of the world.
The shocked quartz pointed to an impact somewhere in the Caribbean. Still, the scientists couldn't find the crater. Then, researchers got a lucky break. In 1978, Pemex, the Mexican oil company, was surveying the Yucatan Peninsula. Geophysical data from the survey and gravity field maps revealed a giant horseshoe-shaped structure buried 3/4 of a mile underground, beneath the sea off the Mexican coast. It was huge, 112 miles across, 12 miles deep, with outer impact rings stretching to 125 miles in diameter.
You see circles around each other like a bullseye. And the rings define the size of a crater. And it turns out that the largest ring was around 200 kilometers in size. And that was exactly the size of the crater which was predicted 10 years before.
It was massive, it was old, and it had all the signs of an impact crater.
They took samples during drilling. And later on the microscope we found shock quartz. By analysis of the rocks we found high abundance of iridium.
The iridium and shocked quartz in the crater matched samples from the KT boundary layer. Scientists were convinced they had found the impact crater. But to be sure, they wanted physical evidence at the surface. They got their break inside a Mayan human sacrificial pit in tropical Mexico. 11:38 p.m. on our clock of Earth's history. 65 million years ago, 70% of all species on Earth, including the dinosaurs, were wiped out. Scientists believe the cause was a catastrophic asteroid impact. They'd unearthed evidence of a massive crater in Mexico's Yucatan Peninsula, buried off the coast, deep underground. What the scientists wanted was real physical evidence at the surface to prove that this really was the site of the KT impact. Chichen Itza in Mexico. The Mayans worshipped here 1,000 years ago, but the land they built on was shaped by an event 65 million years earlier. The area is famous for its Mayan temples and also for its cenotes, or sinkholes. They form when limestone rocks get hollowed out by water, forming caves. As the cave gets bigger, its roof weakens. Finally, it collapses, leaving an open cenote. To the Mayans, they were sacrificial pools. To us, they're pointers to a species-killing impact crater. In 1996, NASA scientist Adriana Ocampo made the connection between the cenotes and the impact. She realized that the pattern of the cenotes across the region was physical evidence of the crater.
The discovery really was like a detective story. And the cenote ring was the last piece of the puzzle that gave credence to the theory.
Cenotes normally occur along lines of weakness or faults in the bedrock. Ocampo realized that the Yucatan cenotes may not be on natural fault lines. The faults could have come from an impact. She studied satellite images of the Yucatan Peninsula and compared them with the oil company's maps. The cenotes were arranged in a semicircular ring, exactly matching that of the impact crater.
Here we are at the rim of the Cretaceous Tertiary impact crater. This cenote is one of many hundreds of cenotes that form a semicircle that is the surface evidence of the Cretaceous Tertiary impact crater.
Finally, scientists had the exact location of the impact. They could begin to build up a detailed picture of the day the asteroid struck. 65 million years ago, a giant lump of rock hurtled through the solar system at 45,000 miles an hour. It was 6 miles wide and weighed about 1 trillion tons, the size of Mount Everest. And it was on a collision course with Earth. It smashed through the atmosphere and crashed into shallow seas at 20 times the speed of a bullet. The impact released 6 million times more energy than the 1980 eruption of Mount St. Helens. It set off a trail of destruction that would end with the death of the dinosaurs.
And you realize that at that size, when that asteroid impacted the Earth, at the moment it started to contact the surface of the Earth, its trailing edge was still up there at 35,000 feet. That's the altitude that jetliners are flying. So we're really talking a massive object slamming into the Earth.
The initial plume of superheated gases and debris incinerated virtually all life in the impact zone. Nothing within a 1,000-mile radius stood a chance.
It literally would have been hell on Earth. This mountain of rock would have immediately, the contact point would have started glowing with a brilliance like the surface of the sun. You probably, just from the heat of the fireball itself coming in, the flesh would have been burned off your body just from the intensity of that fireball itself.
To understand what happened on the day of annihilation, scientists recreated in the lab. NASA's Ames Research Center, just outside San Francisco. NASA scientist and asteroid strike expert Peter Schultz recreates the moment of impact when an asteroid hit shallow seas, just as it did 65 million years ago. First, he builds a layer of sand to represent the land. Then he covers it with water to simulate the ancient ocean.
What we're trying to do is to put an ocean in here. We're trying to cover up the land with a shallow ocean. So this is kind of like something comparable to the impact on the Yucatan 65 million years ago.
To simulate the asteroid impact, he uses the Ames vertical gun. It can fire a projectile at 18,000 miles an hour.
Oh, sweet. Okay. Get her saved. Come on, get her saved.
It's vital to examine the impact in detail, but the scaled-down event happens too fast for the naked eye.
One frame here.
So Schultz records the impact using ultra-high-speed photography.
That is simply extraordinary. Look at that. Oh, okay. Let's see what really happened. Step through this slowly. Oh, let me go back. Look at this. Oh, this is gorgeous. Kapow! Here, now it came in this direction, slammed in. This is now vapor that's expanding, heating up the atmosphere, just turning it into fiery hot, almost as hot as the surface of the sun. It's really intense. This is the part that would have been lasting seconds and then would have translated all the way downrange. And then the crater began to form.
The effect of the impact amazes even Schultz.
If we imagine this being the Earth, our atmosphere, or if we were imagining ourselves in a jet plane 65 million years ago, we'd be flying along and we would be only about less than my fingernail height.
The simulation shows the pattern of debris ejected from the sand and water. The bullet throws up pounds of debris. 65 million years ago, the asteroid would have kicked up billions of tons.
We're talking about 500 billion tons of debris that was tossed out. We saw in the experiment that this was just these were small splatters. But imagine this being the size of buildings, larger than buildings, the size of a small city.
The material thrown up from the crater reached speeds of up to 25,000 miles an hour.
Some of the debris would have actually achieved escape speed. It would have gone faster than the Earth could hold it together, to hold it in its orbit. That material could have made it to the moon. There may be some material sent from the Earth to the moon.
The immediate effects of the impact were devastating. At the point of impact, the temperature hit 16,000 degrees Fahrenheit. It melted surrounding rocks and sent molten bullets flying out at supersonic speeds. Then came a violent and powerful shock wave. Superheated 2,000-mile-an-hour winds hurtled out from the impact site, incinerating everything in their path. Hell came to Earth, and its creatures had no place to run.
This is worse than a horror movie. This is worse than your worst dream. It's very difficult to contain our imagination when it comes to thinking about something this scale.
The initial impact was over, but the aftermath was just beginning. The asteroid landed in water, triggering a gigantic tidal wave, one of the largest the Earth has ever seen. "65 million years ago, a gigantic asteroid smashed into the planet. The impact shot out a superheated blast wave that reduced anything in the kill zone to ashes. But this was just the beginning. The asteroid landed in the sea, generating a huge tsunami. Peter Schultz's recreation shows in miniature what he thinks happened next.
The shock wave from the impact itself actually causes the water to splash out. So we've already created a shock that is the beginning of a tsunami that would have traveled all the way across the Gulf of Mexico. It would have been speeding along and then crashing on the shores in Alabama, Georgia, that whole region, and over on the western side of Mexico.
The tsunami of 2004 was around 30 feet high. The tsunami 65 million years ago would have been 10 times higher and thousands of times more destructive. A 300-foot wall of water hurtled out from the impact zone at hundreds of miles an hour. First, a superheated fireball, then a blast wave, then a mega tsunami. Nothing within the kill zone could have survived the onslaught. Yet far from the impact radius, literally on the other side of the Earth, dinosaurs were wiped out. Something didn't add up, unless the aftermath of the impact was even greater than thought. Back at the KT boundary in Colorado, planetary scientist Dan Durda has unearthed a microscopic clue that could explain how the impact triggered a global catastrophe.
In addition to the iridium that we see in this layer and the shocked quartz grains, we find small particles of soot In some cases, actual charcoal. But the soot we certainly see all across the layer and in all parts of the world. And in fact, if you add up the total amount of soot in that boundary layer, it adds up to something spread globally. It's something on the order of 70 billion tons of soot. And that's roughly equivalent to, all of the Earth's vegetation going up in flames at once.
This layer of soot found in the KT boundary throughout the world can mean only one thing: a global inferno. But just how does a whole planet catch fire? Los Alamos, New Mexico. It's the birthplace of the atomic bomb, but today Los Alamos scientist Kathy Plesko studies a much larger explosion. Here at the Applied Physics Division, Plesko and the team use supercomputers to study how a cosmic impact could incinerate an entire planet. The simulation also reveals for the first time just how the planet burst into flames. The impact was so powerful, it hurled over 500 billion tons of debris into the air.
A lot of it makes it up into the upper atmosphere, and some of it even makes it out of the atmosphere, and it orbits in space for a little bit and then re-impacts into the surface of the Earth somewhere else. So this debris actually went all over the surface of the Earth, and as it was coming back in, just like when you see in a meteor shower, things heat up as they come back in to Earth's atmosphere, this debris would have heated up too, but there was so much of it that it would have heated up the entire atmosphere and started forest fires just from spontaneous combustion on the opposite side of the globe.
For hours after the impact, billions of tons of superheated debris rained down on Earth. It buried the planet in burning rock and set the Earth on fire. Soon, most of the world was ablaze. Many animals far from the impact zone survived the initial blast, only to die in the raging wildfires.
For the dinosaurs, anywhere on the planet would have been lethal. At that point, anything standing anywhere on the surface of the planet, even in Antarctica or Siberia on the other side of the world, would have been in real trouble. It was a very, very bad day for the dinosaurs.
Incredibly, against all the odds, a few dinosaurs did find shelter and survived the tsunami and the global fires. But even their days were numbered. Of all the places on the planet the asteroid could have struck, it hit the worst possible spot. "11:38 p.m. on the clock of Earth's history, 65 million years ago. A massive asteroid struck off the Mexican coast. The impact, the tsunami, and global wildfires that followed wiped out almost every living thing on the planet. A few hardy creatures still survived. But they faced an even greater threat: sudden and dramatic climate change.
The impact lofted all of this ash and debris and dust into the atmosphere, blanketing the entire atmosphere with a thick, opaque layer that made it night for about 2 to 6 months. You couldn't see anything. You couldn't have seen your hand in front of your face on the other side of the world for 6 months.
Dust and ash blocked out the sun. Temperatures dropped like a stone, and kept on dropping, thanks to the impact's location.
If there was one place on Earth that would have been a bad place to be hit, it was the Yucatan Peninsula. The fact is that that area had a lot of sulfur-bearing minerals, and that has longer-term effects on the global climate, as well as immediate poisoning in the area around it.
The blast generated incredible heat. It vaporized the rock and blasted tons of sulfur dioxide into the air. The gas mixed with water in the atmosphere to form droplets of sulfuric acid. And that was a disaster. The droplets were highly reflective. They bounced the sun's heat energy away from the Earth and sent temperatures plummeting.
So at first, you have the dust lofted into the atmosphere, which blocks out the sun. That eventually falls back as the atmosphere convects and cleans itself out. But then you've still got these sulfur oxides up in the upper atmosphere, which reflect sunlight and cool the planet. So this prolonged the impact winter for probably another couple of years.
Temperatures dropped by about 10 degrees Fahrenheit. Forests destroyed by the global fires struggled to regenerate. Eventually, the sulfur dioxide fell to Earth and temperatures returned to normal. But there was a sting in the tail. The sulfur dioxide fell as acid rain.
First, you have this 6-month-long winter where there's no sunlight at all. And then finally, you get a little bit of sunlight and the plants think, oh, good, finally, I can sprout my seeds and grow again. And then the sulfur dioxide falls as acid rain and burns all the leaves off your plants.
The food chain collapsed. The few animals that had survived the blast, the tsunami, the raging fires, and the plummeting temperatures now began to starve. And the asteroid's after effects just kept on coming. Now, global cooling made way for global warming. The rocks the asteroid hit didn't just contain sulfur. They also contained carbon dioxide. Vaporized by the impact, the rocks released billions of tons of greenhouse gases, the equivalent of 3,000 years of modern fossil fuel burning.
The carbon dioxide was the last effect of the impact, and it hung on for centuries, now warming the planet instead of cooling it. So the climate is then artificially warm and not returning to normal values for several centuries after the impact.
The effects of excess carbon dioxide were devastating. Temperatures increased by about 20 degrees over the next 100 years. It was global warming on a fast track.
It was a true ecosystem collapse, something that we can't even imagine at any scale today. And there was no recovery. It wasn't a bad summer. It was a devastating hundreds of years.
Temperatures soared. Much of the land turned to parched deserts. Vegetation died. Plant-eating dinosaurs starved to death. Now the carnivores had nothing to eat. They died too. After 150 million years of supremacy, the reign of the dinosaurs came to an end. But despite the death and destruction, life persisted, somehow. A few species not only survived, they thrived, and eventually evolved into us. 65 million years ago, a giant asteroid hit the Earth. It set off a chain of events that wiped out 70% of life on Earth, including the dinosaurs. But with the dinosaurs gone, a new species of animal, the mammal, took center stage. These highly adaptive creatures were small in size, but eventually they would dominate the planet. One branch would evolve into humans.
The extinction of the dinosaurs clearly cleared the way, if you will, emptied the world of that particular ecological niche and gave the mammals a chance to rise to prominence. And so the extinction of the dinosaurs was sort of the crucible of human evolution, ultimately, if you will. We're here because they're not.
But why did these primitive mammals survive when so many other species didn't? The answer lies in Golden, Colorado. Here, Jalen Eberly hunts for the remains of our direct ancestors. In a layer just above the KT boundary, she's found the fossilized bones of animals that survived the impact, the fireball, and extreme climate change. They were small mammals, the size of rodents. They seem unlikely heirs to the dinosaur's crown. But the qualities that had once kept them near the bottom of the food chain now took them to the top, starting with their small size.
If we compare the KT meteorite impact to, say, something we can envision today, such as a nuclear war, the organisms that would be most likely to survive something like that are going to be the small ones, the ones that can escape the surface in some way through burrowing, living underground. They had a much higher chance of surviving than anything that would be on the surface, such as these large dinosaurs.
And these subterranean survivalists had another thing in their favor. They were omnivores. They would eat just about anything.
The mammals that you have right after the KT impact, such as this fellow right here, Bioconodon, these guys are generalists, meaning they could probably eat a variety of different things. For mammals, being a generalist would be very helpful after the KT boundary because there are going to be a variety of foods on the scene, and I think if you were too specialized, the KT boundary might have been where you met your end.
Mammals had another significant survival advantage. Unlike the dinosaurs, they didn't lay their eggs on the ground or raise their young out in the open, where the predators lurked.
Dinosaurs lay eggs, and their young develop in eggs and then hatch. Mammals, on the other hand, they lay their eggs on the inside, if you will, and their young develop on the inside with that added protection of the mother's body. That probably was advantageous right after the KT boundary because those young just had further protection from the environments, the elements, predators, scavengers.
A few egg layers did make it. Some were the flying dinosaurs who laid their eggs in trees. They evolved into birds. And the primitive reptiles survived, like crocodiles that buried their eggs underground. Along with the mammals, these survivors of the catastrophe flourished. It was the meek, the burrowers and scavengers who inherited the earth. And eventually they evolved into us. It's extraordinary that in part we owe our very existence to one freak event, a cataclysmic impact that turned our planet into a fireball and unleashed deadly global chaos. But if it hadn't, we might not be here at all.